Good morning, everyone. Welcome to the EasyPower Refresher Work webinar series. It's that time of year that we go over the top 10 list for the previous year. And so that's what prompted this presentation. There's some old returning mistakes, there's some new ones, and some, I guess, observations on my part that others would not call it mistakes. So you're welcome to offer your opinion as we go through these. First of all, I'd like to start with a poll question or two. And again, there's no obligation or liability. First poll question is, what is your experience in arc flash assessment? Trying to see if you're a seasoned veteran or if you're just starting. No liability for any answer, just trying to get a feel for where the audience is with respect to the topic. We do supply a certificate of attendance for everyone that joined us today. You don't have to do anything. You'll receive it in the email. And you're welcome to ask questions. May or may not be able to get to them while we're on the line, but I will follow up via email. So it looks like we have a quorum here. Let's see how folks have weighed in. Okay, so it's a pretty good distribution. Excellent. And then the next question is, what is your preferred option as far as an arc flash study? Again, I'll be curious to see how this balances versus people's experience. For those of you that track things, we're still concerned that there's probably less than 40% of the North American market that's in full compliance with an FPA 70E. So that's part of the reason we do this focus on arc flash. So it looks like we have a quorum. Excellent. Here's how folks have weighed in on this one. Interesting. Excellent. Thank you for that. And then finally, which element carries the most weight in deciding to outsource or not the assessment? And, there may be other responses or other answers that are more befitting your situation. Feel free to make entries on the, I'm chuckling because Harold's apologizing for his selection on one of the previous questions, so I won't hold that against him. All right, we're 10 seconds away from a quorum. Yeah, so if you have another answer to this, feel free to use the question box to communicate that. So here's how folks have weighed in. Excellent. I appreciate your participating and helping out. So let's get on with our discussion here. So here's a list of the top 10 mistakes, and we'll be diving into each one. There's some, like I say, returning favorites and some new contribution, and I think each deserve a discussion in the public quorum. So here's my attempt at doing that. So very frequently, in fact, it still surprises me how often people respond that they can't get the utility data from the company for whatever reason. Either they didn't ask, or the company doesn't have the information, or they're reluctant to release the information as requested. Just as a matter of course, as soon as you accept responsibility for doing an arc flash, you should be addressing the utility company and explaining what you're trying to do, so it's not a matter of holding them at large for any reason, just data that you need to do the study. But the thing I want to emphasize here is that you should not use the infinite source. If you use the utility icon in building a one-line diagram with EasyPower, it automatically has very high numbers in it, which we reflect as the source, an infinite source that has its purpose, but not as an arc flash value. Now, the responses you'll get from a utility company can take many forms, and at the very least, you should document it and keep on record what their response is. But these can take a form like the one on the left, where we have different categories and different selections, or a utility letter like the one on the right, where they specifically address what the service is to my location. Very informative, very good information, and in many cases it's more than we need to do the arc flash. But it's helpful in doing other studies, so nothing lost. But in any case, you don't want to use an infinite source. And I say that because an infinite source has its purpose. For instance, calculating equipment duty on a worst case situation, but it's not good for arc flash. And the reason for that is that it trips faster. The protective devices trip faster, and consequently we get a lower incident energy, which is not being conservative. Now, people often ask, what do you do if you can't get the data? Well, I'm going to kind of walk through a scenario that's not necessarily recommended. It's just one of many choices that you can make. But basically, you want to start with a reasonable assumption for the utility current short circuit value for three-phase, and you base that on an educated guess, talking to other companies in the neighborhood that may or may not have done a study. And then let me just show you. And what I want to show is the impact on doing the calculations based upon all these choices. So first of all, I'm starting off comparing the actual data versus an infinite source data. And just for grins, I've made the subsequent circuit identical on both sides. And I've connected the two, which is the way EasyPower won't accept a one-line diagram where there's isolated sources. So rather than have two feeders or two drawings here, I connect them with this virtual cable and leave the switch open. But if you go into short circuit and see what the results are comparing on half cycle current, comparing the infinite source with the actual source, we see that 20,000 amps coming as the real data versus 4.6 million amps. The difference as far as my results is literally only 2 calories, or less than 2 calories, difference between reduced value and the infinite source. But if we look at the results for instant energy, we get a lower incident energy for the infinite source, and that's not being conservative. So if we're going to stay on the safer side, we want to be a little bit more conservative in selecting the value for our realistic source. Now, how do you do that? Well, first of all, I'm going to go back to database edit, and I'm going to build two scenarios. The scenario manager, I've built two values. Let's just reopen one line. I built a value with maximum utility, so I take the 20,000 and bump it up by 20% to get 25. And the minimum, I take away 5,000 amps. And so if I look at these, look at my max, I don't change anything but the value for the utility. So under the base case, I had 20,000 amps, and I based that on the value of this installed fuse. If we look at how the fuse is rated, it's rated for 50,000 amps. So a conservative value might be, for grins, half of that number. So that's where I got the 25,000. Now there may be more accurate ways to estimate it, but that's just where I started. And then I saved in a max utility scenario a 25,000 amp source, and I saved in the minimum scenario a 15,000 amp source. And now I want to see what the difference is at this bus in terms of incident energy. And to do that, I use this. I'm going to go back to my base case. I'm not going to change anything. Select that bus that I'm concerned about. I'm going to go into Scenario Manager, create a comparison report for arc flash, and see which is worse. And so to do that, I've created a report that has the max utility and the minimum utility. And that's what I'm going to exercise for this single bus, LV1. So LV1, the worst case is the minimum utility voltage current, because it's almost 2 calories worse than the maximum utility. Okay, so now I can do the same thing. Now, you might say, well, why get maximum data, the infinite source? And that's the answer to that is for equipment duty purposes. So if we go back and do that same report for equipment duty, let's just pick out this puppy, and do a scenario manager, create scenario report for equipment duty. We see the worst case then this for equipment duty is the max value. So it has its purpose, and it's a good rule of thumb as a backstop for equipment duty calculations. Okay, so that was kind of fun. All right. So any questions on this procedure? The main thing that you want to do is document how your path, whatever you did to make those assumptions. Now, this goes to being conservative in the selection of correction factors. In the new model, 2018 model of 1584, there's a number of correction factors that you can use, either the typical value, which is included in the standard and included in EasyPower, or if you know some value or you want to estimate a worst case on one of these, you can input that data yourself as user specified. Well, the problem is that originally in the 2002 release, we were encouraged to be conservative in our approach to instant energy calculations. But with the advent or the extra testing that was done in 2018, the updated model gave a better match to the data that's been taken, the test data. And so now we're being suggested that we don't have to be conservative or as conservative as we have in the past. One of the examples to this is the classification and understanding the impact of electrode configuration. And the most conservative or the worst case hazard is horizontal in a closed box. Part of the problem is people are unclear as what the definition of horizontal in a closed box. For instance, these buses here are horizontal, but this is not considered to be horizontal in a closed box because the bus butt end of the bus work is within the enclosure. this is not terminating in a barrier doesn't constitute horizontal in a closed box. What is if I have the buttwork of the buses sticking out of the enclosure. So in this case, this would be the most hazardous and the most conservative, but it's not necessarily what you encounter as far as what's your definition for horizontal in a closed box. Likewise, using the worst case, most conservative fault current. In 2002, the suggestion was to use momentary current because it would be the worst case both at fault current. However, in 2018, there's a recommendation that we consider a dynamic model for arcing current calculations because the system has decaying, especially if there's a large motor load or motor contribution, which will decline or decay over a short amount of time. So EasyPower's integrated method recalculates the arcing current for reduced arc current based upon a decreasing or dynamically changing bolted fault current. And so what that means is for the first cycle of the fault, EasyPower will integrate using half cycle value for available fault current. During the next 8 cycles, the tool will integrate the model for the 5 cycle value or the interrupting current calculated for the bus. And if the arc lasts more than those 9 cycles, the arcing current will be calculated based upon the 30 cycle steady state current from the model. So it's agreed the method is less conservative than the previous value, and it will clear up some of the issues we had with lower current. Now here's the soapbox that I stumble over virtually every time the topic comes up. And that is the intent or the activity of using labels for hot work. And a label reflects the standard working distance to remove the cover. In short, in other words, if the cover's on the bus work, the cover's on the panel, they're technically, if it's been installed and maintained per manufacturer's instructions, there's a relatively low probability of arcing fault or an arc hazard if I'm not engaged in moving that any element on that bus. Now, the typical values from the 2018 version are, as I mentioned, for working distance are given in the standard itself. But to do hot work, NFPA 70E requires hot work permit should be used, and that's where you do a working distance calculation for the task that's at hand. Now, this comes to a point ahead in the discussion when some people want to use maintenance mode, instant energy on the label. It's like, I don't think that's a good idea either. And I say that because if my method says, okay, I'm going to compare normal operations to an instant energy based upon maintenance mode, and I'm going to put them both on a label. If I look at the results that I'm depending on, the working distance in both cases is 18 inches. But the task that I'm trying to do under maintenance mode may be something much closer than 18 inches. So while this is erroneous in and of itself, it doesn't amount to the correct calculations for the task or the work that's going to be done. And that's why on EasyPower will create the work permit, and based upon the task that's selected, I can modify or show what the working distance is that my body or parts of my body will be in contact or in the vicinity. And so when EasyPower prints out the results for that work permit, that information will be shared, not only the study and the typical arc boundary for cover removal, but also the working distance for this particular task and the PPE ratings that we need to have when doing that work. And I understand the catch-all, and I don't label that in a negative term, but Article 130.5H in discussing equipment labeling says in a supervised industrial installation where conditions of maintenance and engineering supervision ensure that only qualified persons monitor and service the equipment, the information required in 135.H1 through H3 shall be permitted to be documented in a manner that's readily available to persons likely to perform examination, servicing, maintenance, and operations of the equipment while energized. So again, this is a consensus standard, and that means I can read into it what I feel is the situation for my organization. And this document says I can put whatever I want to on the label and in the documentation that personnel use for maintenance. On the other hand, I better document that deviation or my procedure and make sure that my people are following it as far as training, because I'm going to be on the hook for missing the boat if we have a problem due to miscalculations from the maintenance team. I digress. This is a fun one. And, again, this is a repeat from last year, but frequently I see people they will send their first round of arc flash calculations with the 2-second rule limiting all voltage ranges that they have in their system. And when the question is why you did that, it says, well, 1584 says it's okay to limit everything to 2 seconds. Well, not exactly. It turns out if the incident energy is high due to long tripping times of the overcurrent protection device and the worker has room to escape if necessary, it may be reasonable to limit the incident energy calculation time to 2 seconds. But, and it's not even in fine print, they emphasize using engineering judgment. And I say that because putting a 2-second limit on the calculations prematurely at the very least could obscure problems with series or selective coordination. So let me just kind of show you what I mean. And this is a good example of missing the boat as far as that goes. So bear with me just a second. I mean, missing the boat in terms of what we're trying to accomplish. Now, and this is I don't even remember where I got this example, but I received the one line, went to short circuit focus, look at my arc flash hazard setup, and right away I see everything is listed at 2 seconds. Like, oh, geez. When that's the case, the next thing I want to find is there any place where we have potential for miscoordination? Well, if we look at this, I'm going to fault the bus, look at incident energy. This is a 480 volt system. I guess I'd be better off looking at my range for arc flash. So here I have a 2.4K voltage and 12 calorie PPE, 12 calorie incident energy. On this bus, I have a 480 volt system, and it's tripping on manual time, which is the 2-second limit, and I'm still getting 20 calories incident energy. And likewise on this 2.4K. So my 2.4 kilovolt buses have more or less restrictive incident energy than my 480 volt. And yet I'm limiting everything to 2 seconds. So my question is, how's that coming about? So the next thing I'm going to do is look at the coordination. So we're going to skip over ground coordination for right now. Look at this transformer. Now, in this one line, this load was the only thing showing up for this transformer. So let's go into coordination and look at the plot. And what I see is, now this is a 330 kVA transformer rated at 6%. And so I have a 6x, 6 times the full load current possibility for my protection scheme. And if I look at this line is my transformer damage curve, and this is the relay that's protecting downstream. And sure enough, if I fault down here, look at instant energy, I have a realistic 6,000 amps. I guess I have a problem with 6,000 amps and 480 volts and limiting it to 2 seconds, assuming someone's going to run away before they get hurt. And so what can be done about it? Well, for starters, if I don't need all this capacity on this transformer, I could lower this set point. And just by doing that, I bring my calorie rating down. And if I look at my instantaneous trip on the relay setting, I'm going to not limit the, look at the settings. So my instantaneous trip is at 1,000 amps, which scares me on a 480 volt system. So I'm going to put and so we can see my trip current could be much more reduced or sensitized if I tripped inside of the instantaneous. So now, admittedly, I've taken up a bunch of capacity that could be used, but apparently my loading system isn't taxing my transformer. But now I have much more civil instant energy protection, and I don't have to put on 20 calorie PPE to work on it. Now, whether I want to do that or not, or whether I should do that or not, has a lot to do with what's going on down here. But we show it as just a bulk load. And so questions should be asked before you do something like that. Yeah, so my point is, make sure that if you're doing the 2 second max, that you don't skip the coordination. And so at the very least, even if you have had this relays tested, if you don't want to pay for coordination, if the client doesn't want to pay for coordination because it's been done only a few years ago, just for your satisfaction or coverage, I think you should be doing a coordination check, because there could be data entries that could be caught. There could be data collection problems. Again, the miscoordination if I'm doing my 2 second max prematurely. And so what I recommend, at least do a CYA check with your sequence of events to get a selective coordination check. So let's see what I got for sequence of events. So again, these are very much subjective, and there's nothing that says this is the only way to do it. I'm just offering suggestions that you may want to make sure you're not obscuring miscoordination by prematurely going to 2 second max. And so I'm looking for my sequence of events. And so it could be a very complex system that we're looking at, but at the very least, if I go to coordination, looking at current, I'm going to ask for a sequence of events report to be created. Pick out a single bus, fault it, and then invoke sequence of events on the second row. I will see in chronological order This breaker will trip in 190 milliseconds. This breaker will trip in 35 seconds. This fuse would have tripped in 33 seconds. And then the relay would have tripped in 290 milliseconds. So we have miscoordination just based upon this check. Pick out another single load, fault it. We see we don't have the problem except with the relay. So that again is even if the client didn't ask for coordination, before you start making recommendations on instant energy protection, you may want to double check your coordination. Okay, invariably, someone will come in and say, well, it's been 5 years since we did the study. Nothing's really changed, so just rerun the new equation and send me the labels. Well, you may be correct that nothing's changed, but did anyone swap fuses out or replace fuses and maybe only replaced a single phase? Or maybe didn't even make sure they had the same manufacturer in the fuse positions? Or was there someone tweaking the relay or power circuit board settings without realizing they were changing the instant energy calculations? Any large loads added or deleted? So at the very least, when you're doing a follow-up to instant energy calculations, you might want to do a sequence of events check. Again, it seems kind of common sense, but it frequently comes up that for whatever reason, the client may not have wanted to pay for it. So at the minimum, you want to have protective device details verified. Make sure all fuses match in all 3 phases. And again, taking a picture is a good way to verify that. Verify relay settings, utility. Now, utility companies can have changes in their data, and they're not obligated to tell you about it. So checking with the utility on all updates is mandatory. And then you want to make sure you have scenario configuration scenarios for doing labels and comparing that against what your label conditions were from the last study. This is a real common mistake because there's a lot of confusion, and especially based upon our understanding or misunderstanding during the 2002 standard. And that is the IEEE 1584 recommends including the main if there's not an arc barrier between the main bus and the incoming conductors to the main breaker. The problem is any arc on the incomer to the main will generate a plasma cloud, and the resulting fireball could engulf anyone working in the switchboard enclosure. In addition, if the plasma ball can touch electrified buses, the arc can propagate itself up or downstream. And this is not an exaggeration. There's many videos on YouTube that verify this very problem. So just for clarification's sake, if you're going to remove the cover and work on the bus while it's hot, there's 3 different examples. And obviously this is a single phase domicile or domestic installation, but it illustrates the point. If I'm looking at the incoming connectors to the main, if I can see the metal to that incoming breaker, here we have a bottom fed and a top fed, and all 3 there's bare conductors that I'm sticking the incomer to, and I'm going to be working on this bus on the other side of that breaker. There's nothing to protect me from an arc initiating on either side of the main, and I'd be in the firing line. Now you say, well, the National Electrical Code just required a coverage over the incoming conductors for the termination to prevent inadvertent contact. Doesn't that count? So The answer is no, it's not good enough. Here's an example of a piece of plastic that covers the incoming conductors to this main breaker, and it will reduce considerably the potential for accidentally touching these phases without knowing it. But it's not an arc barrier, so this doesn't cover it as far as instant energy protection. Now, an argument could be made, well, it's going to, most arc flashes are initiated by an inadvertent touching the bus, so why doesn't this count? Well, it will count as far as reducing the frequency of arcing faults, but it doesn't protect once that fault's established. So take it upon yourself to make sure you're justifying using the main. I've seen companies that were sequestered, it was kind of a nice term, sequestered the main outside of this main panel. And the fact was they put another enclosure with the disconnect or the main breaker here, and then piped in the results to a main lug only bus. And in that case, we would have the main and could include it. And the documentation covered sequestered breaker as part of the design. Now again, this is another case of trying to limit the cost on the study where people say, well, no, I don't need to worry about equipment duty tests because the client didn't ask for it. I think you really want to consider this step as a make sure you're not making a mistake step, because an arc flash incident energy is based on the condition that each element would operate per the manufacturer's test or spec. And if I haven't verified that, then I'm not on very solid ground when I go to claim that this protective device is going to bring down the incident energy for somebody working downstream. And as we kind of showed, running the equipment duty will compare the manufacturer's rating against the worst case fault current. The operation is not guaranteed, the operation of the breaker is not guaranteed if the component is over-dutied. Now, it's relatively simple both to verify, and I've seen situations where people, granted this is a new user mistake, but they didn't realize that equipment duty was that easy to do, and they just didn't know to click the button. So here's what it looks like. And I don't mean to harp on this, but it just doesn't make sense to do a study without one simple button click to verify equipment duty is adequate. Okay, so what is being done when I click on equipment duty? So just so you know, if I go to short circuit focus, looking at three-phase bolted fault all the buses, that illuminates this little token on the second row called equipment duty. And when I click on that, what it does is apply a measurement against the threshold for every one of these devices. And that threshold is determined under short circuit options control down on the bottom third, that by default, we're going to set a threshold of negative 10% from the manufacturer's datasheet rating, and then flag the results. And so I've got three cases where I will see a result. I've got a positive number, which means it's some component on this bus is over-dutied. It won't meet the manufacturer's spec, or it exceeds the current that it's rated for is lower than it will see at a worst case fault. I can see red numbers with nothing there, which means I didn't properly set up this breaker because it's not doesn't result in this threshold test. And then I can see results negative rather a red indication with a negative number, which means it's inside that 10% threshold, but it's still compliant. Now, this is just a display on the one line. If I go to short circuit reports, I can create an equipment duty report and include all voltage violations or warnings, or I can include all devices. But by so doing, my list of windows shows an equipment duty report. And sure enough, on the main switchgear, the breakers are all okay. They're rated for 37,000 amps, and I'm going to see it initially 19,000, and they're all well outside of that 10% threshold. But the bus work itself, the way I set the model up, I had a rating of 15,000 amps, and that's being exceeded during a worst case fault. Now, so this is something that needs to be addressed, whether it's a data entry problem or if that's actually something that's been in place for 25 years and nobody caught it. It needs to be discussed. And then we see that everything else is in good shape until we get down to that main bus, and I see BL2 is rated for 24,000 amps, and in a worst case, it's going to be hit with 22,000, which means it's still compliant, but it's inside that threshold. Okay, equipment duty, I can't overstress how important it is to include this in the study. The report, literally it's one button click, and the report is made for you. All the reports can be exported to Excel or Word or printed as is. Okay. And I make a note that Smart Duty compensates for X over R differences. EasyPower calculates the X over R for every bus in the system, and wherever there's a protective device where the manufacturer has tested it within a certain X over R value, EasyPower will compensate so that we're doing an apples and apples comparison during this test. Still, I see people come at me and say, my client wants both the HRC category and the instant energy on the label. What should I do? Well, you can quote to them per 70E starting in 2012 that all PPE labels can't have both the instant energy and the lookup PPE value from the standard. Now, they've taken off in 2015, they've taken off the reference to HRC, which is hazard risk category, and they changed these tables' name to PPE category, but still they say a label may not have both the instant energy and the category number for PPE. Now, it's all well and good that someone comes and says, nope, it's my plant, I want my labels, everything is and my safety manual is based upon the HRC reference, and so I don't want to change all my manuals. My people are being trained to utilize the HRC category. Again, it's a consensus standard, and so this allows me to define my own category table and just define the instant energy and the PPE rating without referring to the HRC. So this is kind of a workaround that's relatively simple, but you're going to have to define your own category table and again, not refer to the old-fashioned HRC. Most important in this discussion is how I train the people to utilize the information that's on the labels to best protect themselves. And therein lies the real proof of my system. If personnel understand what the instant energy is and what the PPE category they're going by means, then I'm in pretty good shape. But I may want to be auditing that. my suggestion is the industry is going to maintain or try to accomplish alignment with NFPA 70E. So sooner or later, you may want to consider doing that. This was an exercise I ran through, and this is not cast in stone. It's just a little exercise I did where I use the conditions in the PPE table to determine how they calculated instant energy. And if I did a category 1 comparison, it came up with 4 calories as the rating that I should have on my PPE. If I went in and just calculated the instant energy based upon the same parameters, the model allows me to have less than 1 calorie per square centimeter PPE. So what I see is there's a fair amount of guard bending in the lookup table, which you would expect, and that's why just crossing the boundary there is a dicey operation. So that was on the low end. Same thing was true on the high end. Whereas at 15 calories and 35,000 amps, we had a minimum 40 calorie exposure. And just using the model, it was 9.6 calories per square centimeter. Now again, this can be put on there, the label if I want, but bear in mind that it says non-compliant with NFPA 70E specifically. Now, just a thing to be aware of is to prevent having to replace this label when it starts to fade or every 5 years or whatever. I could use something like the QR code that reflects the most up-to-date information for doing calculations and advise people, my workers, what the PPE is or the instant energy is or changes in the system. But this can be updated daily if I wanted to, compared to the label being a hard copy. So this brings up the fact that compliance to NFPA 70E is not a one and done event. It really requires the ability to include or be aware of the continuous process of improvement, both in the body of knowledge about arc flash and the equipment that's available in the industry for protection. So part of your electrical safety program should be the evaluation of the changes in the standards themselves and result in system modifications to improve employee safety. Again, my recommendation is to set a timeline to ultimately be in alignment with NFPA 70E, and then make sure you're training your workforce to recognize which PPE is required for the indicated instant energy level. Now this last mistake is frequently encountered even by seasoned veterans, and part of it is a lack of ability to kind of look at the insight that the tool provides. But complex systems may have multiple energy sources during a fault. And usually the slowest device to trip is used for calculated trip time. And this is where the integrated method comes into play. And frankly, it works against us. So not too long ago, I had an engineer call me and say, Jim, I'm adjusting this relay and I know it's set for 1800 amps, but why is the arc flash so high when I only have a fault current of 4.1 kiloamps? Like, well, you want to identify the source of the fault current, and you want to make sure it's in the path of the last device that's being tripped. So let me show you what this came up as. This was a fun discussion because it took a bit for me to kind of realize what was going on. And what made it even more fun it was a real system, and we were looking at the trip session. That's sorry about it. Okay, so what the question was is like, okay, I know this is set for 1800 amps, and yet when I fault this bus, which has 4,000 amp fault current, it's not tripping the relay. So, and we're getting very high instant energy. He says, and when I make adjustments on the relay, it doesn't change this number. Well, the first question that I asked was, well, what is faulting? What's even giving us that time? And if we look at our short circuit options, he already had his time limit set up to 2 seconds. So that made me nervous and concerned about coordination. When I go to the arrange for arc flash, I see that upstream trip device is 9005.1.11. And the next question was, well, what's the sequence of events telling me? So if I pick out a single bus, current, fault the bus, and then look at sequence of events, this relay is tripping at 16 milliseconds. Where's that 900111? So I'm going to go look at find. Nine. Looks like it's a fuse. And sure enough, it's this fuse right here, which is giving me 184 amps and 806 amps during a fault. So if I take this offline, if I open this breaker, and go back and look at the result of my instant energy. So what the problem ends up being is a generator that's online during that fault. And so if I go back to my arrange for arc flash and take that generator open, 9005, I'm sorry. So it's the fuse back on this generator. So if I open this fuse and go back and look at my arc flash, I get a valid or pretty nice 6.6 calories per square centimeter. And now my relay is the tripping device. But then I looked up and I said, well, this is a 25,000 amp, 25,000 volt bus, and it's an open air. It's outside of the range of IEEE. So what's going on here? So let's go back to instant energy calculations, short circuit options, arc flash hazard tab, advanced. So the tool is automatically doing Ralph Lee method rather than IEEE 1584. But Ralph Lee method is for three-phase open air above 600 volts. And this is an open air bus. So what happens that? Well, EasyPower allows me to apply the NFPA 70E 2009 recommendations for lookup for greater than 15,000 volts. And by doing that in a single phase to ground, I get for this bus a 0.4 calorie instant energy in recognition that this is outside of the NFPA 70 boundary and EEE 1584 recommendations. So it's outside the range of 1584. So there's two things to be learned. One, current well, he was obscuring the calculations because we limited it to 2 seconds. And if we had left it alone, we could have seen that that fuse was online forever, and we needed to take it out of the circuit. Secondarily, this was a single line to ground fault that we should be aware of, and that was obscured because we had the 2-second rule in place. So this phenomena, I guess is what I would call it, is something that we should be aware of when we have constant energy sources that don't necessarily clear during the 2 seconds or during the time, because they don't shut off. Their fault current is lower than the protection that's being installed in the system. So in this case, with the utility open, we still have a 8-calorie exposure because we're have too low a current coming out of the photocells. Anyway, and this would be where the 2-second limit would be appropriate for faulting on this bus with this low current. So a couple things were learned along the way. So that's my list of 10 mistakes. But I would add one more, and that is make sure you follow the hierarchy of risk control method, and don't just put on more PPE if that's what you're trying to do. You're better off considering using technology to improve the protection of personnel rather than put on just more PPE. Thank you for your attention. Copy of the slides are available in the handout section, and I look forward to talking to you down the road. Have a good day.